Hello, everyone. Welcome to the lecture video for Chapter 8. I'm coming at you live from my daughter's bedroom. Why am I in my daughter's bedroom? It's because my wife is home from work and needs to watch Bravo at full blast. So I'm here with Elsa Piggy Bank, Frozen 2, unopened, what do you call these? Nightlight, pink bed sheets. That's where I'm at. But enough about me and my situation. Let's talk about you and your situation. You want to learn about multifactorial ANOVA. I can help you with that. So all of the tests we've been doing so far with t-tests and with ANOVAs have been situations where there's only one factor. So what does that mean? You might have people from different grade levels, like freshman, sophomore, junior, senior, and you want to know who sleeps more at night. So that would be one factor with 4 levels: freshman, sophomore, junior, senior. Or you could say, look at student athletes. It's very interesting. Do student athletes, they have a complicated role. How does their GPA look? Do the teams differ? Like, is the basketball team, golf team, and tennis team different in terms of their GPAs? That would be one factor. What team are you on? With a level for each team you decide to collect data on. But what happens if you want multiple factors? Like with student athletes, maybe the average GPA for basketball players is not as high as the golf players. But what if it really matters if we're talking about men's basketball and women's basketball? So you have 2 factors. You have what team is someone on, and you have gender, male or female. For the purposes of this class, I'm just gonna do the basic assumption, usually, unless you're explicitly going out to recruit non-binary and gender fluid and whatnot people, you're not going to end up with enough people in that group to be able to do an analysis, because you won't be able to make a reliable estimate for any of your stuff. So I'm going to help myself to the binary male-female categories. But if you have 2 different factors, you have what team are you on and whether you're male or female, and each of those factors have multiple levels, then you might end up with a situation where you have several sample means, but you want to know whether one set of sample means is different from another set of sample means. And in multifactorial ANOVAs, that's what a main effect is you say, take one of the multiple factors. What sport are you in? What gender are you? Pick one. Let's say gender. Is there a main effect of gender? That would mean, do men overall differ in their GPA or whatever the dependent variable is compared to women? So you ignore everything about the other factor, like what sport are the men and the women playing. You're just saying average across all of the different sports teams and just look at average male GPA versus average female GPA. That would be the main effect of gender. If you want to do a main effect for team, you would that's like asking which teams have different GPAs from one another, ignoring the difference between men and women, just looking at the differences between the teams. Those are main effects. You just you choose a factor and you average over the other factor. And then you have what makes multi-factor ANOVAs really tricky, but also really interesting and worthwhile, is you have the interactions. An interaction is a notoriously difficult concept for newcomers. And what it basically means is that one factor depends on another factor. So the effect of what sport you're playing has on your GPA depends on whether you're a male or female. Or if you're male or female, how that affects your GPA depends on what sport you're playing. That dependency between the variables is an interaction. The factors interact, the factors depend on each other. So let's look at an example. So this is a study on pain, and you have people reporting how much pain they're in. And one group of people take a placebo pill. That's an inert pill that doesn't actually work, but the patient thinks it does. And you have another group of people, well, there are actually two groups apiece. The one factor is whether you're in the placebo group or a group that gets a real medication that's 50 milligrams. Within these two broad categories, you have two groups apiece. You have a male group and a female group in the placebo condition, and you have a male and female group in the 50 milligrams condition. So you have 4 sample means overall. You have the average pain reported by men in the placebo group, the average pain reported by women in the placebo group. You have the average pain reported by women in the medication group, and you have the average pain reported by men in the medication group. 4 different groups. Now, is there a main effect of group, placebo versus 50 milligrams of a real medication? Yes, there would be, but it's important that you average over the other factor. You combine men and women when you're assessing if there's a main effect for one factor, you average over the other factor. So compare the placebo average and the 50 milligram average. That's easy. The placebo average is basically a 10 because they're both groups in this condition are right on top of each other. For the 50 milligram condition, you have to kind of split the difference. So it'd be probably around 18, 17, 18. So it does look like there's a difference. We'd want to test this difference, this main effect, going from here about 10 to here about 17. We'd want to do a statistical test that takes into account sample size and whatnot. But just judging off of the chart itself, if this was a large sample, you'd be pretty confident in saying there is a main effect of group, placebo versus 50 milligrams. Now, is there a main effect of male versus female? You see that men report a 10 on pain in the placebo group and a 10 in pain in the 50 milligram group. So if you average that together, that's about a 10. You meet in the middle, it's a 10. Women are also a 10 in the placebo group, but they're at a 30 in the 50 milligram group. So you split that difference, that would be like 20, I guess. Yeah, it'd be about a 20. You meet in the middle between the two female groups, the placebo group and the 50 milligram group, women. So basically the middle of this line versus the middle of this line, assuming this is a sample with a large enough groups supporting each mean, then yeah, you'd be pretty comfortable saying there's a main effect of gender. Women report more pain overall, but that's why interactions are so important. An interaction has to do with the extent to which the factors depend on each other. And you can see clearly from this chart that there is an interaction because men and women react exactly the same with the placebo pill, but women respond to the actual medicine way more than men. And really, all the difference is coming from this medication by gender interaction. If there were no interaction, then you might see just 2 parallel lines, like going from the placebo to the 50 milligram group, men and women react basically the same. Or you would, I don't know, you basically, if it's a 2x2 design, like one factor with 2 groups and another factor with 2 groups, you would, if there's no interaction, you would just see 2 parallel lines in some form or another. I should probably have an example of no interaction as one of the pictures. One thing you'll see a lot on stat exams that trips everyone up, and yes, I put them on my exams too, because it really tests your understanding of a main effect and an interaction, is this X-shaped interaction. And this is an interaction because, men react completely differently to the medicine in this alternate example. Men report lots of pain on the placebo and less pain on the medicine. Women report little pain in the placebo, but lots of pain on the medicine. That's as big of an interaction. It's like night and day and people flipping over. You get completely different results depending on what level of what factor you're in. So yeah, definitely interaction. The lines are not parallel, they're intersecting. But is there a main effect of medication? Is there a main effect of male versus female? This is what trips a lot of people up, because you got to remember when you're assessing main effect, you're asking, when I go from one level of one factor to another level of that same factor, completely averaging over all the levels of the other factor, is there an overall increase or decrease? So let's look at placebo versus 50 milligram. In the placebo group, there's two sample means. Women report about a 10, men report about a 30. Split the difference or average over that, you get 20. Overall, in the placebo group, there's about average of 20 when you average over women and men, because we're talking about a main effect of placebo versus 50 milligram. Do the same thing in the 50 milligram group, and you still get a 20. Women report a 30, men report a 10. Average those together, you get 20. 20 versus 20, that's no difference at all. So there's no main effect of placebo versus 50 milligram. And the key to understanding that is realizing that you're averaging over the other factor. Let's ask, is there a main effect of men versus women? Again, no, there's none. If you look at men in the placebo group, you start at 30 and they go down to 10 in the 50 milligram group. If you average those together, 30 and 10, you get to 20. With women in the placebo group, they report a pain of 10, and in the 50 milligram group, they report a pain of 30. You meet in the middle, that's 20. An average of 20, when you average over placebo and 50 milligram, and an average of 20, it's no difference at all. You have to average over the factors. So I mentioned statistical testing, and I talked about what a main effect is and what an interaction is. But you have to test them. You don't usually just look at a table and just say, yeah, that looks significant to me. You actually test it. I don't go over the math behind it for a multifactorial ANOVA. I just do the math for you, and you get over here to the ANOVA table. I think it's good to learn the math eventually. In practice, if you're doing research, you're probably going to feed these numbers into a spreadsheet and then tell the software, do this analysis on these data, and it'll give you this as an output. So you have, just like all the ANOVA tables you've seen before, you have on the leftmost column every source of variation. You've got group, placebo versus 50 milligrams. You've got gender, male versus female. And then you have the interaction, the group by gender interaction. And then you have residual. Residual means leftover. Once you've accounted for some of the pain by taking into account whether someone's in the placebo or the 50 milligram group, after you've further accounted for some of the variation in pain by accounting for whether someone's male or female, and you account for how much these two main effects depend on each other with the interaction, after that, you just have a little bit of leftover variation in pain that you can't account for with the two main effects and the interaction. And then the total is just overall, how much variation is there in reports of pain. We do the typical stuff. You have degrees of freedom. I'm not going to go over how to derive those. Mean squares is just sum of squares divided by degrees of freedom. So 5 divided by 1 is 5, 12 divided by 1 is 12, 100 divided by 20 is 5, so on and so forth. And for each of these sources of variation, you have an F value, and you're going to compare the F value as the ratio, the mean squares of group and the leftovers. So 5 divided by 1.29, that's the mean squares for group, and the mean squares residual is 3.85. The mean squares for gender is 12. You divide that by the residual, 1.29, you get 9.24. Divide 5 by 1.29, you get 3.85 again. Oh yeah, I know why it turned out different. I was kind of confused for a second. So that's what each of these F values says. For this source of variation, how much bigger is it than the leftovers? And this is the mean squared. So it's like the average leftovers or the average deviations due to group, the average deviations due to gender. You divide each source of variation, the main effective group, the main effective gender, the interaction, the group by gender interaction, divide each of those by the residual, and that gives you a measure of how many times bigger than the residual is each of these numbers. 5 is 3.85 times bigger than 1.29. 12 is 9.24 times bigger than 1.29. 5 is, again, almost 4 times bigger than 1.29. These F values represent how much bigger each source of variation is compared to the leftovers. And the F distribution is the same. You plug in degrees of freedom for the source of variation. For group, it's 1 degrees of freedom. For the residual, it's 77 degrees of freedom. F distributions have 2 different slots for degrees of freedom. So plug in 1 for the numerator degrees of freedom and 77 for the denominator degrees of freedom. How likely is it to observe an F value of 3.85 or higher when you assume the null hypothesis is true? It's about a 3% chance. In other words, if you assume there's no difference overall in groups, then there's about a 3% chance that you would observe a group effect this large or larger. Same logic for everything else. You assume null hypothesis is that being male or being female makes no difference for pain. You plug in 9.24 on the F distribution with degrees of freedom of 1 and 77. How likely is it that you'd observe an F value of 9.24 when you assume there is no difference, so it should be 0? You get 0.3%, or in decimal form, 0.003. So an even more unlikely observation, because according to the null hypothesis, each of these F values should be about 0. Now you can see something as high as 1, 1.5, maybe 2. If the null hypothesis is really true, you might just happen to notice, or you might happen to observe a difference between groups just because of sampling error. But sometimes the difference between groups gets so large that you can't just chalk that up to sampling error. You have to say, well, the null hypothesis probably isn't true if it's this improbable that I'd see something this big. And then for the interaction, the null hypothesis is that there's no group by gender interaction. So, null hypothesis says this F value should be 0. You put 3.85 on the F distribution with 20 degrees of freedom and 77 degrees of freedom. That's why the P value is different. I was kind of confused. The F value for group and the interaction are the same, but they had different P values. I was kind of like, did I make a mistake? But no, they have different degrees of freedom. When you plug different degrees of freedom into a distribution, it changes the shape of the distribution, and thus it changes the probabilities of observing different scores on that distribution. But yeah, there's less than a 0.001%, 0.001 probability of this, of seeing an interaction this big or bigger when you assume the null hypothesis is true. And then we don't do hypothesis testing on the residuals. It'd be kind of dumb to do that because, of course, there are residuals. You can't account for everything. And then this is just a total. How much do we have left here? Oh, okay. This is the last slide for this one. Much like a regular ANOVA, once you get a p-value from the overall ANOVA table, it doesn't tell you which groups are bigger than which. Since each of these factors only have 2 levels, then if I say there's a main effective group, placebo versus 50 milligram, then you know whichever one has higher pain levels is significantly higher than the other because there's only 2 levels. But if one of these had like 3 levels, like let's say basketball players versus football players versus tennis players, so there's 3 groups and sport is the factor. If you get a statistically significant result for a factor with that many groups, then you don't know necessarily which groups are statistically different from which. You just know that there's at least one significant difference among those groups. So just like with a regular ANOVA, if you want to come down and test specific hypotheses, you have to actually do a post hoc test. That's where you actually say, okay, I explicitly like want to tell is, are men in the 50 milligram group different from the women in the 50 milligram group? And the amount of tests you're doing, you'll want to correct for that using something like the Bonferroni correction I talked about in one of the previous lectures. But again, if each factor has 2 levels, you don't really need to do that. I should probably have something with like 3 levels to kind of make that point. But yeah, that's basically everything for this chapter. So you should be fluent in the language of talking about factors and levels of factors. You know, a t-test is you're testing whether a dependent variable changes along one factor with only 2 levels. The ANOVAs we learned before is asking whether a dependent variable changes over the levels of one factor, but there's more than 2 levels. There's at least 3 levels. That should make sense to you by now. And that's the level of fluency I expect you to have on an exam. You should be able to understand what a main effect and an interaction is. And if I show you a chart like this, or if I show you a bar chart of sample means, you should be able to tell me whether there looks to be a main effect or interaction. I should be able to show you an ANOVA table and ask you questions like, if I explain what the data is, and then I say, is one group have more than the other group than the dependent variable? You should know to come find where that group is on the ANOVA table and scooch over to the p-value. If p is less than 0.05, say yes. If it's not less than 0.05, say no. There is no statistically significant difference. You can't conclude that there's a difference. You need to be able to read ANOVA tables. All right, that's everything for this chapter. I will see y'all. I think there's only 2 more chapters after this. So if you've been binging this, it's almost done. So sit tight.